Quadcopter Sensor System Group. I'm Kim.
I'm Ivan. I'm Dustin.
So we'll start off with a question. What do these images have in common? The answer. The answer is that they represent really large problems over really large areas. And modern technology has gotten to a point where we can come up with a more effective solution for this.
So we propose a remote data gathering solution to implement wireless sensor network over large areas. What we provide is multiple sensors on the ground that collects data and sends that data to a drone using Bluetooth.
So we have two basic components for our system.
Let's go back one. So ask questions. Why is that a good idea, bad idea? Let's challenge that concept a little bit. When will that be a good option to use as opposed to other options? Okay, well, raise your hand and ask the question. Raise somebody who had a question. Raise your hand, ask the question, and then they'll answer it. Challenge them.
So why is this a good solution?
Okay.
You haven't thought about it. Give them a counterpoint. Why? And challenge. Not necessarily arguing with them. Just give them a counterpoint. Why not do it another way? Give them another option of doing it.
So why is this better than me hopping on my bicycle and losing a few pounds biking around to pick up all this information?
So do you want to bike like 20 times a day?
Me personally?
Yeah.
Seriously, so why not, I mean, it's a wireless system, why not transmit all the data wirelessly? Why will this specific solution, what scenario will this solution be more effective? Question.
So this solution is more attractive when you're comparing it to a data transmission system over a very long range, because that's very power intensive. And if you think about what we want to start looking into now, it's really remote areas or really large areas, and it doesn't make sense to consume that much power when you want to really reduce how much battery you're draining for your system, because then you increase your maintenance. So
Let's say I can put a mesh network together and they can talk to each other and they communicate to the network out. Why not do that?
Because it's also power intensive to transmit over a longer area. Because here we're...
Okay, so mesh networks are often being put forth as an option, but they're very difficult to get low power because they all need to kind of listen all the time to each other, right? And there are certain situations where you just cannot get the wireless to communicate with each other. You have to go into a location. Like we're working in a wineries, and we put sensors in there and they can talk to each other, but there's certain rooms and there's so much concrete around that specific building that there's no way in heck that one can get into that through wireless. So in that case we will have BLE transfer, but for example you can think of a scenario that something is sitting in a lake somewhere and there's whatever reason there's interference, and you can have this drone going specifically to that center part and that feed information. You need to be able to articulate that scenario, because then people will really say, oh, okay, we thought about it, right? Okay, good.
So these are the basic components for our system. On the quadcopter side, we're going to have a PSOC 4 BLE with a PSOC 5 for data storage. And then on the ground sensor side, we're having sensors, Bluetooth, and power management. So our goals this quarter are to demonstrate an autonomous flight. So we're going to have a quadcopter flying through an agricultural field, picking up data from the sensors that are in the field. And then we're going to show how it's more effective in terms of power.
So this is our communications diagram. For the beacon, we will be having two sensors and a rotary switch communicating over SAR ADC to the PSOC 4 BLE beacon. And we'll also be having a humidity and temperature sensor that will communicate over I2C to the beacon. It will also communicate to flash memory using SPI, and with all this, it will send all the data over to a PSOC4 BLE receiver on the drone over a 2.4 gigahertz frequency over Bluetooth. And then from there, the receiver will send the data over to a PSOC5 over UART, and then the PSOC5 will store this into an SD card over SPI.
For power on the beacon side, we're going to have a combination of batteries and solar cells for our first prototype. And this is so that in case our solar cell doesn't work out or just it's nighttime, the battery can still power up the system. Then we're going to send these two inputs into a power management IC, which is from Cypress. And then we're going to send it from the storage capacitor out to all of our peripherals.
So on the beacon side, we have a rotary switch that'll change the address of the beacon so that the user can manually see which beacon or which data it's gathering from. We have 3 sensors that'll take measurements from environmental measurements. We might add a pH sensor maybe, and when the PSOC acquires measurement from the sensors, it'll also timestamp those data and store that data to flash memory. And when it connects to a drone, it will get those stored data from the flash memory and send it through Bluetooth. On the receiver side, once that data is received, it'll also timestamp that data when it received that data and send it through PSOC5 and store it in an SD card.
So this is our state diagram for our beacon. It will initially be in a sleep mode, and then after, I think, every 30 minutes, we're gonna get data, and then off that timer, we're going to start advertising the data. If it doesn't find a connection within a certain time period, then it'll go back to sleep mode. If it does connect to the drone, then it'll send the data and then disconnect and go back to sleep mode. This is a state diagram for our receiver. So it will initially be in sleep mode, and we're using an Intel Edison that controls the drone. So when that's on, then it will begin the scanning process for the sensors or the beacons. If it connects, then it will receive the data and promptly disconnect afterwards. And then it will send the data to the SD card and then go back to scanning shortly after.
So you guys need to wrap up in like 5 minutes, 4 minutes?
Okay. So for this project, we've been using a new kit from Cypress called the Energy Harvesting Solar Powered IoT Device. And it's got a lot of different sensors on it, and it can run off of the solar panel. So we've been using it to test the capabilities of the solar panel and the power management IC that we decided to use.
So the cost for the beacon, it's around $55. The most expensive part seems like they're pretty equal. We could reduce the cost for the main hub if we use a PCB antenna instead. We're gonna decide when we test that out.
That's per beacon. Why do you need 6 solar cells per beacon?
Each little solar cell is around 50 microamps of power.
Okay.
So if we want to operate the system at its maximum power draw, that's how many we would need.
Might I get like a big solar cell, like one big one?
Yeah, we also have a big one to test, so we'll consider that.
Right, on the receiver side, it's around $35. Most expensive part is the main hub because of PSOC5 and the SD card.
So these are our quad goals. We're pretty on schedule right now. We started during winter break with all the basic research in board designs and PSOC to VSOC Bluetooth communication. I think right now we're working on our final design board for the beacon, and then we'll be working on the receiver side shortly after.